Let's break down a key concept in engineering: concentricity. It's part of GD&T, the language engineers use to make sure parts fit together perfectly. Concentricity is all about making sure round features share the same center, like planets orbiting the same sun. Imagine a donut with an off-center hole. That's poor concentricity. In engineering, we want the centers of circles or cylinders to line up exactly. For example, a shaft fitting into a hole. Both axes must align for smooth operation. Even a tiny misalignment can cause big problems, so we set limits on how much off-center is allowed. This principle applies to everything from wedding cakes to blender motors. Anywhere perfect alignment matters. Concentricity keeps rotating and stacked parts running smoothly, preventing wobbles and failures. It's the unsung hero behind reliable, high-performance machines. Why is concentricity so important? First, it ensures smooth rotation. A wheel that isn't concentric with its axle wobbles, wears unevenly, and causes vibrations. In high-speed parts, like turbines or hard drives, perfect alignment is critical for balance and efficiency. When features are concentric, mass is evenly distributed, preventing destructive vibrations. Think of a washing machine shaking when clothes are off balance. That's what poor concentricity does to machines. Good concentricity also makes assembly easy. Parts fit together smoothly and reliably. It's essential for automated assembly lines, where precision is non-negotiable. Ultimately, controlling concentricity boosts reliability, reduces wear, and extends product life. Whether it's a drill bit or a gearbox, concentricity keeps everything running true. It's a fundamental requirement for robust, dependable engineering. How do we show concentricity on a blueprint? With its own GD&T symbol, two circles, one inside the other, a bullseye. This symbol appears in a feature control frame, a rectangular box with three compartments. The first compartment shows the concentricity symbol, telling you what's being controlled. The second compartment gives the tolerance zone, a cylinder centered on the datum axis with a specified diameter. For example, 0.05 means the axis must stay within a 0.05 millimeter diameter cylinder. The third compartment names the datum, the reference axis everything aligns to. If you see datum A, look for the feature labeled A elsewhere on the drawing. The full frame might read concentricity symbol 0.05 datum A. This means the feature's axis must be concentric to datum A within a 0.05 mm cylinder. It's a precise universal instruction for machinists and inspectors. That's how concentricity is communicated in engineering drawings. So, how do we check if a part meets a concentricity callout? It's tricky. You can't use calipers. You need a coordinate measuring machine, CMM, to map thousands of points and find the median axis. This process is complex, slow, and expensive. Because of this, concentricity is rarely used in modern GD&T. Instead, engineers often use position tolerance, a simpler, more practical control. Position tolerance uses a different symbol and controls the axis directly, making inspection much easier. You can check it with simpler tools or a basic CMM program, saving time and money. The key difference: concentricity controls the median axis, while position tolerance controls the features axis. For most real-world applications, position tolerance is sufficient and far easier to verify. That's why you'll see position tolerance used for coaxiality much more often than concentricity. Let's recap. Concentricity ensures perfect alignment of cylindrical features. It's vital for smooth rotation, balance, and easy assembly. On drawings, look for the bullseye symbol in the feature control frame. The frame tells you what's controlled, the tolerance, and the datum. But measuring true concentricity is tough, requiring a CMM and lots of time. That's why position tolerance is now the go-to for most alignment needs. Still, understanding concentricity is key to mastering GD&T and building reliable machines. Keep practicing, And soon this engineering language will be second nature.